see one of the uninformed search strategy that is called as a iterative deepening search, or it is also called as a iterative deepening depth first search strategy. So in the previous lectures, we have seen regarding to a depth first search, we have seen one of the technique that is nothing but a modification in a depth first search strategy, that is nothing but a depth limited search. But the problem in a depth limited search is nothing but whenever we are assigning, or we are not analyzing a problem properly and we are assigning a depth limit something, that is nothing but depth limit of suppose 1 or depth limit up to a 2, then under most of the cases, if we are not analyzing problem properly, then we are not able to search, or we are not able to find out a goal state. Under that situation, the depth limited search is not proper to conduct a searching process. To overcome this drawback of depth limited search, the next technique device that is called as a iterative deepening depth first search strategy, or iterative deepening searching strategy. So today we'll see how it is working. So suppose we are taking one of the example, we'll take one of the tree. Suppose node A, which is nothing but your initial node. Suppose we are having a node B, we are having a node C, we are having a node D, we are having a node E, we are having a node F and G. So as per your usual method, this is usual method of your depth limited search. You are assigning a labels, label 2, label 3, label 4 and label 5. So these are all the labels in a iterative deepening searching process, or we can say a tree. So as per a depth limited search, we are assigning a certain limit, and for that the trees available to conduct a searching process is up to that particular limit logically. So it is most of the time creating a problem. Suppose we are taking an example, suppose depth limit 2 is available, so the tree available for carrying out a searching process is up to a limit 2, means the nodes available are nothing but A, B, C. Okay, these are the 3 nodes available. If the goal node is not available under this particular logical tree, then a depth limited search will declare that the tree is not having a goal node. So this is most of the times problematic if you are not analyzing a problem properly and putting a depth limit alpha is equal to something. Okay, suppose now this particular tree is having a goal state as E. So if at first time, whenever we are conducting a iterative deepening search, suppose you are assigning a depth limit alpha is equal to 2, then I'll explore this A, I'll check whether A is a goal node. If A is a goal node, print succeed and stop there, there is no question. If A is not a goal node, then I'm interested to check whether it is having successors. So I'm checking it is having successor B and it is having successor C. So suppose at this moment I'm putting this C first into a stack and then I'm putting B into a stack. So now topmost element of my stack is nothing but a B. So I'll explore this B, okay, as it is a topmost node. So I'll cross check it across a goal node. If it is a goal node, print succeed and stop there. If it is not a goal node, then I'll check its successor whether it is having successors. At this moment my depth limit is equal to alpha is equal to 2, so it is not having successors because tree logically available to carrying out a searching process is up to this. So I'll say that there is no successor available and I'll go for the next node which is available in the stack. So stack is having a element C. So I'll cross check it whether it is a goal node. It is not a goal node. So I'll print the particular tree is not having a goal node, but the tree may be having a goal node. So I'm interested to increment the depth limit by 1. So I'll get a sanction for depth limit increment by 1 and my depth limit assign is nothing but a 3. So now tree logically available to carrying out a searching process is up to this level 3. So I'll explore this. I'll again conduct a depth first search. So I'll explore this it is not a goal node. I'll explore these two. C will be at the bottom, B will be at the top, so I'll explore this B. B is not a goal node, so I'll explore its successors. These successors will come at the top of my stack. Suppose I'm putting this D first and I'm putting this E next, so E will come at the top of my stack. So now I'll cross check this E. Okay, if it is a goal node, S, it is a goal node, so I'll print succeed and stop there. If E is not a goal node, then I'll close that particular node. I'll check whether it is having successor. It is not having successors, so I'll close it and I'll check the next topmost element of my stack. If D is a goal node, then print succeed. If D is not a goal node, then don't go for a D successor, because this is a last level, this is a leaf node. I'll explore C. I'll check whether C is a goal node. If C is not a goal node, then I'll check whether it is having successor. It is not having successor. Okay, now all the nodes in this particular logical tree are over and your stack is empty. Means that particular node is not available under this particular depth limit alpha is equal to 3. So I'll again demand for the next increment, that is alpha is equal to 4. So next the tree available to carrying out a searching process is this. Okay, if the goal node is available under this particular limit, then it's okay, print succeed and stop. If not available, I'm again demanding for your limit increment, that is alpha is equal to 5. In this way, in an iterative deepening search, iteratively I'll explore each level one by one, not at a time. So this is a little modification in the depth limited search so that it can help to achieve a goal node in a proper way. Okay, so this is all about your iterative deepening search, which is also called as a IDS search or IDS, okay, which is coming under a uninformed search strategy.